And it's my privilege to start off this seminar series for you. I think it's a great initiative by the Nigerian chapter, and I think policy dynamics has a unique ability to help the world, and Nigeria in particular, but the world in general, with the tools and the skills to solve many of the world's most serious issues, challenges. Anyways, this presentation, I'm from Policy Dynamics. It's a small company in Canada, in Ontario, Canada, and we do management consulting. And like I said, I specialize in system dynamics, and my hobby is mentoring young people or anyone who's interested in learning system dynamics quickly and learning the best practices of system dynamics and solving problems with system dynamics. Anyways, this presentation is called The Building Blocks of System Dynamics. It's going to have, I guess, 5 parts. The first part is the system dynamics building blocks: stocks, flows, converters, and connectors. It's interesting that system dynamics is only got these 4 ideas, 4 features, and you can build almost any kind of complex model of any kind of system that changes over time with just these 4 different types of building blocks. So I'm going to show how to build a simple model in system dynamics software, and then I'm going to convert it to Excel and show you how the mathematics works in Excel, which may be more familiar to you than the system dynamics software, and also it can be useful for me to estimate parameters of a system dynamics model. And then I'll show you the same model as a causal loop diagram. You may be more familiar with the qualitative work of system dynamics with causal loops and feedback loops, and you can see the feedback loops much better in a causal loop diagram, I think, than in a Vensim stock and flow model. And then I'll get into a little discussion of the model, Nigerian population demographics, and I'll show the Vensim model and the Excel model, and we'll have a little discussion, time for discussion at the end. So it was funny, you know, like I was telling Kalichi before we started that I just registered for a user name for ChatGTP, and so I asked ChatGTP to explain system dynamics, stocks, flows, converters, and connectors in terms of the demographics model of Nigeria. And this is what it said. I thought this was really good. It said, sure, here's an explanation of system dynamics, stocks, flows, converters, and connectors in a demographic model of Nigeria. Stocks in a demographic model of Nigeria. Stocks might represent the population of different groups, the number of births and deaths, and the number of migrants entering and leaving the country. These stocks are components of a system dynamics model that accumulate or deplete over time. Flows in the demographics model of Nigeria might represent the rate of births, deaths, and migration in and out of the country. These flows are components in the system dynamics model that influence the rate of change in the stocks. Converters. In a demographics model of Nigeria, converters might represent the impact of healthcare and education on the population growth rate, the influence of cultural factors on family planning and fertility, and the effect of economic development on migration patterns. These converters are components in a systems dynamics model that convert one type of input into another type of output. Connectors. Feedback loops are an important connector in system dynamics that represent how changes in one component can affect the behavior in another component, which in turn can impact the original component. In a demographics model of Nigeria, a feedback loop might represent how changes in population growth rate can impact the availability of resources such as healthcare and education, which in turn can affect the population growth rate. Delays are another type of connector that represent the time lag between an action and its impact on the system. In a demographics model of Nigeria, a delay might represent the time it takes for changes in healthcare or education policies to take effect on the population growth rate. Using these system dynamics concepts, we can create a model of the demographics of Nigeria that simulates the interactions and relationships between different elements, such as population growth rate, healthcare, education policies, economic development, and migration patterns. This model can help policymakers to understand the impact of different factors on the population to make data-driven decisions to optimize the country's development over time. I thought that was really, really good. And that's what we're going to do today. We're going to talk a little bit about demographics, not quite as complex a model as this is suggesting, but it's correct that this model could be expanded quite a lot to discuss things like healthcare and education. So we're going to have a simple model. I'm just going to model one stock, the stock of people. I'm going to have an inflow of births, an outflow of deaths, and a flow of net migration. And I'm going to have three parameters. I'm going to have a birth rate, fraction of people migrating out, and life expectancy. So let me show you how I'm going to build this model. So I'll just go to Vensim. Okay, I'm going to open a new model. And this is the Vensim software. Vensim is a company that produces system dynamics software, and I use it. It's got a very nice, what they call personal learning edition, which is downloadable for free if it's used only for academic and learning purposes. And it doesn't have all the features of the full professional edition, but it's got a lot of very good features, especially for academic purposes. So I'm going to start by creating a new model. So I'll just create a new model here, and I'm going to run it for 100 years with a step time of 1 year. And I'll get into that, what that means later. And I'm going to use Euler integration, which is a methodology for solving integral equations. And I'll get into how Euler integration works in a minute as well. So I'm going to do this. I'm going to set it up, and now I'm going to put out first a stock. A stock is an accumulation of something you're interested in. So I'm going to call this stock population. And so it's something. One good way to think about stocks is that if it's a state of the system, and if time changes, if time stops, that is, if time actually just stops, the population will still be around. So there may not be any births or deaths, but there'll still be people if you just imagine the idea that time would stop. Anyways, but time doesn't stop, so it changes with time. And the way it changes with time is by having flows into it and out of it. So the first flow that I'm going to introduce is births. And you just do this, and then you connect this flow to births, and this little cloud represents something that's outside the model, and so this is the boundary of the model, and so births is included in the model, but the things over here are not included that impact the birth rate. And then the next thing I'm going to do is I'm going to add the deaths, and that's a flow out. And then I'm going to add the last thing is I'm going to add out migration. Okay, so now I have the basis of a model in terms of stocks and flows. And now I'm going to add parameters to the model. And so the first thing I'm going to add is an initial population. And then I'm going to add a birth rate. And then I'm going to add a life expectancy. And then I'm going to add the fraction of people migrating. And then I'm going to add, the last thing is a migration rate. Okay, and now we have to connect these elements together, and we use this arrow connector, and we're going to connect the birth rate, obviously, to the births, and the population to the births. And I'll show you why that is in a minute. We'll also connect the population to the deaths, because you can't have deaths if you don't have people. And so I'll connect the life expectancy to the deaths, and I'll collect the outmigration to the population to the outmigration, and the fraction of people migrating to the outmigration, and the migration rate to the fraction of people migrating. And now I'll add a couple more things that may be a little less intuitive, and that is I'm going to add the life expectancy to the fraction of people migrating, and the life expectancy to the outmigration, and the fraction of people migrating to the deaths. And the reason I'm doing this is because the fraction of people migrating is the fraction of people over the life of those people in terms of migrating. So that's how I have this idea that I need to know the life expectancy of the people to know how many of those people will migrate. And similarly, I assume that the people who don't migrate will stay in the country and will eventually die. So that's unfortunate, but it's the truth. And the last thing I'm going to do is I'm going to add the population to the initial population to the population. Okay, so now we have the basis of a model. And now I'm going to do a few things with this model. I'm going to click on this function, f at x function key, and it'll identify all the variables in the model that haven't been defined yet. So I'm going to define these models, these parameters, and using equations. These equations are generally simple arithmetic. They can be more complex, but generally system dynamics uses fairly simple equations to define things. So the births, I'll start with the births. Well, let's start with the initial population. So the population is equal to the births minus the deaths minus the outmigration. And we specify the initial value here as the initial population. And we're going to make that another important thing about system dynamics is that you calculate everything in terms of things you can measure. So this is going to be people in units of people. And you want to make sure that your units make sense and they're consistent. So this is the population. And then I'm going to calculate the births, or give a formula for the births. And the births is just the population times the birth rate. And this will be in people per year. And so this is a flow, and so it has to be over time. And as I say, if you stop time, the births stop. So that's how you know it's a flow. Okay, and then the deaths. The deaths is a little more complicated. So as I said, it's the population times 1 minus the people who don't, people who emigrate, or people who migrate. So it's 1 minus that number, because that's the people that stay, divided by the life expectancy. And again, this is people per year. And then we have the net outmigration, or the outmigration, and that's equal to the population times the fraction of people migrating divided by the life expectancy. And again, that's people per year. So now we have the stocks and the flows defined. And the last thing I want to define is this fraction of people migrating. And so this fraction of people migrating is equal to the migration rate times the life expectancy, and I'll show you why that is. This is also something called a dimensionless variable because it's a fraction. It's just a number between 0 and 1. It doesn't have it's dimensionless. Okay, so the migration rate is something that I looked up, and the migration rate in Nigeria can be assumed to be 0.3 people per 1,000 people per year. So this is the migration rate I'm going to use. So this is in terms of people per year. So this is 0.3 people per 1,000 people per year. And so that leads to the migration rate, leads to the fraction of people migrating, leads to the out migration. So then I don't know what the initial population is, but I'm going to give it units of people. And I'm going to give life expectancy. I'm going to give it units of years. And I'm going to give the birth rate. It's also going to be people per year. Okay, so that's the units that I've put into the model, and now we can actually check the units to see whether we've got a correct formulation. And the system, Vensim has this nice feature called units check. So I will do a units check, and the first thing it'll tell me is to back up my model, which is a good thing. So I'll back up my model and I'll call it population. And then it'll tell me that there's already, okay, now it's going to do a units check, and it says the units are okay, which means that everything's good with my equations. However, if sometimes you'll find that it'll give a message that your units aren't okay, and you have to go into the equations and see whether your units need to be redefined, or if they're defined, or if the equation is defined inappropriately. Okay, at this point, I'm going to change a little bit. I'm going to go to Excel now. And what I did is I went to a website called Our World in Data. Our World in Data is a very good website for providing data on a lot of things. I used it a lot when I was studying the COVID crisis. It had the number of cases and the number of deaths for every country in the world, which was very useful for my modeling. But it also has the demographics of every country in the world. So I downloaded the file for all the countries in the world, and I took out the population of Nigeria. So this is the population of Nigeria from 1950 to 2021. And that's the most recent data they have in Our World in Data. So now I'm going to build a model in Excel that matches the model in Vensim. And the first thing I'm going to do is I'm going to add a title for population. And I'm going to add every variable in a system dynamics model can be thought of as a column in an Excel spreadsheet. So if you're ever trying to explain system dynamics to someone who doesn't know necessarily what system dynamics is and is trying to understand it, you can just say that it's basically the columns in a spreadsheet. So I'm just filling in the various parameters right now. So I'll say these are the constants or the parameters. So all these I've already talked about, so I don't have to talk about them again, except for this one thing. I haven't talked about it yet, and this is the time step. And time step is very important because the smaller the time step, the more accurate the modeling or the calculations, the numerical calculations. So in this model, we're going to use a time step of 1, which represents 1 year. because that's the way the data is given to us in a year-by-year basis. But it's not going to be as accurate as if you gave it a smaller time step, like a quarter of a year or an eighth of a year. So that's an important factor that I'll get to. So the first thing I'm going to do is I'm going to provide an estimate of the initial population. So I'm going to put equals and I'm going to put B2, and that gives me the initial population. And then I'm going to estimate, I'll put in an initial birth rate just to start with. And I'll put in the migration rate of 0.3 divided by 1,000. And then I'll put in a migration, I'll put in the life expectancy. I'll say the life expectancy is 50 years to start with. And this is just a starting point for the model. And I'll calculate the fraction of the people migrating as the migration rate times the life expectancy. Okay, so now I have the parameters of the model defined. Just to start with, I'm going to calibrate the model to find more realistic values. Okay, so now I'm going to calculate the births. And the births, as we saw, was the population times the birth rate. And now we have the births in 1950. And then we calculate the deaths, and that's equal to the population times 1 minus the migration fraction divided by the life expectancy. And then we have the migration per year, or they have the deaths in years in 1950. And the last thing we'll do is we'll put the out migration, which is the population times the migration fraction divided by the life expectancy. Now, there's one last thing that I need to do before I guess I can do one more thing. I can calculate now the population in 1951. And if you remember the stock equation that was in the Vensim model, we have the stock is equal to the population in 1950 plus, and this is the tricky part, the time step times the births minus the deaths minus the out migration. And that gives us now the population in 1951. Now, I do have to do a few things before I can extrapolate this into the future. The first thing I have to do is I have to anchor these parameters in these equations. So I do that by putting a $ between the letter and the number of the parameter values. So here I'm going to put a $ between J and 2. And so here I have a $ between J and 6 and between J and 8. And that anchors the parameters so that when I cut and paste or copy and paste them down, they will stay at those anchored values rather than copying the formula down with variables. Okay, so now I have the anchored values, and I'm going to now calculate the births in 1951 and the deaths in 1951 and the out migration in 1951. And now I can cut a copy and paste this for the whole duration of the data. So I go down here, I can okay, so now I have a model, and let's just take a look quickly at the comparison between the data. I'll call this, actually, to make it easier, I'll call this model population. And I have actual population and model population. So I drew a graph that compares the actual population and the model population, and I get a graph that looks like this. And of course, you see that the model population is not very close to the actual population. And what I want to do is I want to get this pink line to be pretty similar to this blue line, which is the actual population. And I'll do that by what I call calibrating the model, which I'll show you in a minute. But how I do that is I do something called this minimizing the sum of the squared error. So first of all, I calculate the squared error, and then I calculate the sum of the squared error. So the squared error is just the actual value of the population minus the model population, close bracket squared. So that is the squared error is 0 for the initial value, but it's going to be much higher for the other values. So if I copy and paste that down, I now have the squared error for every year of the population data. And now I'm going to take the sum of the squared error, and I'm going to take the sum of all of these squared error values for each year, and I'm going to put that in this cell, and I get a very large number, as you can see. So now I'm going to use something called a solver, which is a built-in, an add-in for Excel. And I'm going to do something. I'm going to minimize this cell. So I'm going to minimize this cell. I want to get the minimum squared error, sum of squared error, and I'm going to change just 2 parameters. I'm going to just change the birth rate and the life expectancy. And I'm going to try to get a match between the model data and the actual data. So if I run the solver, actually, yeah, that's not good. Okay, did I do something wrong? Oh yeah, I didn't put the, I didn't anchor the step time. Okay, so yeah, you can see that Excel, you have to do some manual work, and you can make mistakes. But generally, if you understand system dynamics, you can figure out your mistakes fairly easily. Okay, so now I have this model, I think, correct. And if I run the solver again, okay, now I got I think a reasonable value. So now you can see that I get a pretty good match between the model and the data. So now I'm going to do something. I'm going to go back to my Vensim model, and I see these blacked out variables. That means they're not defined yet. So I'm going to define them by going to the Excel spreadsheet. I'm going to copy and paste the birth rate into the Vensim model. So there's the birth rate. I'm going to cut and paste the life expectancy into the Vensim model. And I'm going to cut and paste the initial population into the Vensim model. But one thing I have to do is Vensim doesn't like delimited commas in it. So I have to delete the commas. And now I have the model defined with the parameters defined. And now I just run the model by clicking the simulate button, and I can look at a graph of the population for 100 years. So there's a graph for 100 years. So let me just do one last thing. Let me go to the settings, and let's type in the start date of 1950 and the end date of 2050. Okay, so that'll give us a 100-year period. And if I run the model and look at the population, you can see the population growing to up to about a little over 400 million people by 2050. Okay, so that's a simple model of the population. So I'll go back to my my PowerPoint presentation, and as you see, hopefully you'll be able to get the slides after the presentation, and you can see what we did. So here's the model, and then as I said, I collected time series data. I converted the Vensim model to Excel, and then I found the parameters to match the model to the data, and then I pasted the parameter values into Vensim. So that's the process that I used to estimate the parameters. And one thing Kalichi reminded me of, that if you buy a professional edition of Vensim or a professional edition of Stella, one of the other products that's used for system dynamics, or if you use something called Insight Maker, which is a free system dynamics software, you can actually do that calibration of the model in that software rather than using Excel to do it. But one of the things is that the Vensim PLE, which I work with, doesn't have the calibration feature. That's in a higher level model, higher level software package. So I don't have the ability to optimize or calibrate a model in the Vensim PLE. But you would have it in, say, Vensim 6 or higher. So here's the Excel model as I went through it before. Here's the model comparison to the data, and here's the population projection till 2050. Now, one of the things that you have to understand with system dynamics is that you can project into the future, but it's not. It has to be understood that this is not really a prediction. It's a projection of a model or a theoretical concept rather than a prediction. And so the reason is that things will change. So let me just go to one more thing. Let's talk about causal loop diagrams. So causal loop diagrams are a simple way of looking at a model. They don't have to be simple, but in this case, it'll be fairly simple. And there's two things that are important in a causal loop diagram. There's link polarity and feedback loops. And I'll get into that. And then there's two types of feedback loops: the reinforcing feedback loops and balancing feedback loops. So let me just show you. This is a causal loop diagram for the model we just built. And so the loop polarity is shown. The variables are connected by arrows, and then the loop polarity is either S for the same or O for the opposite. And for example, in this case, the life expectancy, if it goes up, the net migration will go up, and if it goes down, the net migration will go down. Similarly, if the population goes up, the births will go up. And if the births go up, the population will go up. So S means they're moving in the same direction. But look at this, we have O here. So if the deaths go up, the population goes down. So we have an O here, and that means it's a negative polarity. And if the deaths go down, the population goes up. So we have these different relationships in the polarity of the connections. And then we can see feedback loops. So we see this loop that the more population, the more births, the more births, the more population. And that's a feedback loop as defined in system dynamics. And in fact, it's a reinforcing feedback loop. That is that it's growing exponentially, and if you look at the polarities sum to a positive value if you multiply them together. But it's pretty easy to trace through the model and realize that this is a reinforcing loop. The other loop is a balancing loop. And in this model, there's two balancing loops. There's the balancing loop of deaths, and that means that the population goes up, the deaths go up, but the deaths go up, the population goes down. So that means that it's not reinforcing, it's balancing. It's more of a heading towards an equilibrium here rather than reinforcing an exponential growth. Similarly, there's net migration, which is a balancing loop. So I define them as balancing loop 1 and balancing loop 2. Now, in some of the softwares like Stella, you can determine loop dominance. So what's the dominant loops in the model? And in fact, in this model, the way Nigeria is set up, the birth rate and the births is the dominant loop, and as we saw, the population is growing exponentially. In say Canada, the deaths might be more of an influence over the population rate, and or the life expectancy might be more of a factor. So this is it could be a different dominant loop for different countries, for example. But one thing about causal loop diagrams is it's very easy to see the feedback loops, which are important in system dynamics, and I think it's easier to see them than in a stock and flow diagram. But they're basically two types of modeling. This is also a qualitative model. There's no numbers attached to it, whereas in a stock and flow diagram, you define the model in terms of units and equations and numbers. So it's more of a quantitative model. Okay, now I'm going to look at a slightly more complex model, and this model will involve demographics. So here we have an idea that we have three populations instead of a homogeneous population of just people. We have children aged 0 to 14, we have adults aged 15 to 64, and then we have elders that are greater than 65 years old. And I built a Vensim model, I converted it to Excel. I'm not going to show very much about this. I did some parameter estimation, and then I'll show you some results. So I'm just going to go through this quickly. This is the model of the demographics. As you can see, it's more complicated. It's got the same basic features as the original population model, but now it's got children as a stock, adults as a stock, and elders as a stock. And you can see there are many different arrows that are crossing, which is difficult to read, but basically it's basically the same model. And then I converted this to Excel, and this was a much larger Excel spreadsheet. You may not be able to see it, but all of these variables here from K to the end are actually parameters in the model, and each one is a row column, as I said. And then here's the squared error for elderly, and the squared error for adults, and the squared error for children, and the TSSE is the sum of the squared errors, which I minimized, and I got the parameters of the model that matched the data. And here is the match of the data. So here's the match for the elders, and you can see that it's a pretty good match between the model and the data. This is the adults and the model and the data. You can see that this is not quite as good a match, and I think this is because the death rate is not a constant, and the life expectancy is not a constant, and not the life expectancy. The death fraction is not a constant. So you see that this is not quite as good a match. And if you look at the children is also not a great match. But one thing I wanted to show you in this graph that I think is very interesting is you can just barely see it. But if you notice, there's a slight inflection here that the number of children is no longer growing at the same rate as it was in the previous years. So in the model, we assume that the children are growing at the population of children is growing at the same rate throughout the whole period. Whereas in the data, you can see that the blue line of the data is showing a slight inflection point just starting, that basically the number of children being born in 2021 per adult was slightly less than the previous year. So we might be seeing heading towards some kind of equilibrium in the longer term. And here's the graph of the results in Vensim. And one of the interesting things here is based on the model projections that the number of adults will be around 225 million in 2050, and the number of people, children between 0 and 14 years old, will be about 200 million people. So that is a huge number of children that are going to be dependent on the adults for their livelihood and their food and shelter. So this could be a significant issue for Nigeria in the future, and we can discuss this at the end of the presentation. So, as I said, there's some things that we can change. So, for example, in this mental model that I'm using, we assume the parameters were constants, but we know that the birth rate is changing, and the life expectancy is changing, and the net migration fractions change over time. So really, those are maybe a better assumptions, but they require a lot more modeling to try to figure out what they are, and to really tease out why the birth rate's changing and why the life expectancy is changing. And as I said, I showed you the original model, which was a single stock of population. In the second model, I showed children, adults, and elders as a subpopulations. And you could break those down to actually being, actual each year of life. And then the last thing was, there's an assumption here of exponential growth, and we know that this cannot go on forever. You just cannot have exponential growth indefinitely. So there's going to be limits to growth. And that's what I was sort of indicating, that possibly we're seeing in the data a slight change in the number of children being born each year. And that might lead to a limit in the population in the long run. Now, one of the things that Kalichi wanted me to mention was the model boundary. And the model boundary is an interesting idea, because you can build very, very complex models and try to model too much. And the way system dynamics does this is it has a problem focus. So it looks at building a model to solve a problem, and it believes that the structure determines the behavior. So it wants to build a model with sufficient structure to identify the behavior of interest. And I often talk about, the way I look at system dynamics is that it tells you where you are today, how you got there, and where you're headed if nothing changes. And if you don't like where you're headed, you can maybe get to a better future by changing the structure of the model, or changing the assumptions that you're using in the model, or changing the policies that you're using in the model and in real life. And then the other idea is complexity. You want to keep the model. This is a classic statement by Einstein. You want to make it as simple as possible, but no simpler. And that's important to recognize, that you really want parsimony. You really want to keep it simple if you can, but you need to be no simpler than you need to be, because you have to identify the problem and solve the problem you're interested in. Okay, another thing that we can note is that this structure that I showed you for population, and it can be used for many other models, many other systems. So the classic one is the bathtub with a faucet and drain, and that's something that's taught to basically to initial people learning system dynamics. But there's also, you can look at lakes and rivers as models like this, with a stock of water in the lake and flows in the rivers. You can look at a bank account with interest deposits and withdrawals, in a similar model. You can look at a balance sheet of a company with assets as the stocks, and profit and loss as the flows. And you can also look at government debt and taxes as being an inflow, and expenditure as being an outflow. So this one model can be used for many different types of problems, and that's the power of system dynamics, is that it's used it can be used for many, many things. It's a very general concept. And as I said, it just uses those 4 things: stocks, flows, converters, and connectors. And it can model many, many different things. In fact, I believe it can model anything that changes with time. Okay, now I'm open to discussion. So hopefully we have enough time for a nice discussion about the implications of this model, maybe any questions you have about it.
Great, thank you, Ivan, for the wonderful presentation, and thank you for touching on a couple of questions that I had regarding your presentation. So there are a couple of questions in the chat. I'm going to begin with the first one. So Johnny is asking, why did you go to the length in order to calculate the birth rate by incorporating the migration, that's the net and outflow rates? If you understand that. So why did you integrate the migration as part of the birth rate? If that's the question.
Yeah, well, I don't know if I really used the migration rate to calculate the birth rate per se. I assumed a migration rate, and then I calculated a birth rate and a life expectancy to match the data. So I don't really think there's a direct connection between the migration rate and the birth rate, except through the data and through the stocks of population. So like I said, the purpose of system dynamics is to model a real system, a problem, and I think that when you want to build confidence in a model, it's useful to be able to look at the history of the system and do a good job of matching the model to the history, and that'll give you confidence to project the results into the future.
Great, thanks. Johnny, do you want to open up your mic and then ask a question?
Yeah, so my question was not relating to the birth rate, it was for the death rate.
Oh, okay. Well, like I said, the way the death rate is based on the people who are in the country, and basically, the number of deaths is based on the number of people in the country, and so I assumed that if people didn't migrate out of the country, they remain in the country, and eventually they will die. So that is what I assumed. So 1 minus the migration rate is the percentage or fraction of people who remain in the country, and they will eventually die after a life expectancy. And then the migration out is the fraction of people who migrate out over the life expectancy of the people who are in the country. So for example, people can migrate out at age 40 or 45 or 65 or 15, but it's over the whole lifetime. I wanted to know the fraction of people that migrated as a general number, an average for all the population. Does that help, Johnny?
Yes, but I have to process first, but I understand the logic about it. Thank you.
Okay, I hope that helps. Yeah, think about it some more. And like I say, this is one way to formulate it. Another way to formulate it is to use rates, to have a death rate and a migration rate. And you can do that, but sometimes the arithmetic doesn't work out quite well, and you have some kind of a double counting problem. So that can be an issue. So I like to do it this way to make sure that I'm getting my units correct.
Thank you.
Yeah, thanks. Johnny, you also had another question. Do you want to ask that as well, or?
You can go ahead, because I don't have them in front of me.
Great. Okay, that's fine. Is there anyone that has a question to ask Ivan? And just for those asking, the recording will be available on the Society's YouTube channel, and there will be a blog post on the Society's website. Okay, Dr. Philip, please, you can have the floor. Yes, Philip, you can open up your mic and speak if you want to.
Yeah, hello, can you hear me now?
Yes, yes.
Yes.
Thank you, sir, for the presentation. I really love it. I'm trying to look at the assumptions you have made so far, and I'm interested as in, do you consider the population, the male and female population? You know, National Population Census 2006, which was the last one in Nigeria, we have the number of female more than the male. Now, considering the population, how it's increased, you said you assume that you make some assumption about the growth rate. But I'm just curious about how do you able to consider the male and female in the population? Thank you, sir.
Oh, okay. Yeah. That's that would be a slightly more complex model. It's not much more difficult, but basically, yeah, you could build a slightly different model which separates men and women, and separates out instead of having a birth rate, having a fertility rate, which would be the number of children per woman, which is commonly a measure that people use to measure population growth. That's a slightly more complex model, but it is very useful. And I think, you know, in a model that involved education and healthcare, I think that would be very important to model out women and discuss the particular problems of healthcare for women and the particular problems of education for women. I think that, you know, maybe I'm wrong. I can't be an expert. I'm not an expert in this, but I understand that education for women will lead to fewer children, possibly, and possibly a better healthcare will lead to fewer child fatalities or birth fatalities. And so that may also lead to fewer children. So in the long run, people would maybe not feel necessary to have so many children, because their children would be guaranteed to live their very good life, and maybe women with education would be able to have more opportunities to get ahead in their careers, for example. And I think that's a particular problem in Western countries today, is that the population actually is declining in many countries, and they can't support their population. That is, the birth rate is less than the life expectancy in terms of death rate, and so the population is declining, and they haven't been able to develop any effective policies to encourage people to have children. And so it seems to me that eventually those countries will be decimated by, if they can't change that policy, if they can't get people to have children, the number of people in those countries could drop to be very low. And also it would lead to a very difficult demographic, because, for example, the elderly in my country, Canada, is growing very fast, and there's fewer people, younger people, to take care of them, and so there's a real problem with the healthcare system because of the burden of the elderly people on the healthcare system and the lack of young people to do the healthcare for them. So those are the kind of demographic issues that I think are raised by this kind of model. I'm studying some of them myself, but I think I think that those are assumptions that I think, you know, I'm not addressing in this model. It's just an introduction, but I think they're very important questions, Philip, and I'd be very happy to work with you or work with anybody on those kind of issues.
Right. Thanks, Ivan. I think we're almost out of time. Yeah, Johnny, do you want to quickly go, and then let's see if Ivan can respond.
Thank you, Kelechi. So, Ivan, I have a question in terms of the definition of the parameters, or parameterize the variables. So I just wanted to ask, is there any advice, general advice or procedure that you can offer to do that? But at the same time, I'm assuming that to have that kind of knowledge, you have to have the knowledge of the subject matter around which the parameters are actually defined.
Yeah, I think one of the things that I think is important to recognize in system dynamics is this model boundary idea. And the model boundary, it can be thought of as things that are inside the model, which are endogenous variables, and things that are outside the model, which are exogenous variables. And basically, the endogenous variables that people have some control over, in the sense that they can change their policies and have some control over what's happening inside a system. The exogenous variables are assumed in system dynamics to be outside the system, outside the control of the system. And so basically, the model and the system reacts to those things rather than it can influence them. So I think the model boundary is really important when you're defining the parameters, to make sure that you're defining the parameters in a way that gets to the point of what do you have control over and what do you not have control over. So for example, in the previous discussion, we were talking about healthcare and education. I think the government of the day has control over those things, and those things should be in the model. But maybe, maybe they don't have control over, for example, the pandemic or something like this that could happen. So they have some control over how they respond to the pandemic, and that's important to measure. But maybe there are things outside of the system that you need to relate to, that are parameters that need to be measured, that impact the system. When you go inside the system, I think it's fairly reasonable to think of system dynamics as being a pretty simple approach to looking at what affects what. And what I often recommend my mentees to do is ask the question why. For example, the birth rate. If we want to put that as an endogenous variable, put it inside the model, we say, well, why is the birth rate changing? And then we say, well, maybe it's education, and maybe it's education of women. Okay, well, why is that changing? And maybe it's because women are demanding more opportunities. Okay, well, why is that changing? And maybe that's exogenous. Maybe that's not in our control. But anyways, if you keep asking why, you'll get to the root of the issue. And definitely you can model too much, but I think that often you get to the real heart of the essence of the problem by looking at the parameters and the variables, and asking the question, why are they changing, or why is this happening? Does that help, Johnny?
Definitely. Thank you, Ivan.
All right. Thank you, everyone. Thank you, Ivan, for the great presentation. And just so before we wrap up, this is the first of the training series that will be organized by the Nigerian chapter. And you can send an email to the Nigerian chapter, nigerian@systemdynamics.org. For those who have joined and then who registered for this, we will share the presentation slides and also the link to the recording when it's up on the YouTube channel. Thank you all for attending. Ivan, any last words? Or
yeah, just a last word is, I hope that that Kalichi and Bunmi will share the video with me, and I'll post it on my LinkedIn page. And if anyone wants to reach me through LinkedIn, I'd be very happy to connect, and they can see some other videos I've done that are posted on my LinkedIn page.
Right.